In this lesson, we're looking at the washer method for the volume of solids of revolution. In the last lesson, we focused on the disk method. And this lesson is kind of similar, except that you can see we want to subtract out a portion of our region. And a lot of these shapes are going to look like a disk, mainly because there's an empty space between our axis of revolution and the equations. So the disk method can be extended to cover solids of revolution with holes by replacing the representative disk with a representative washer. The washer is formed by revolving a rectangle about an axis as shown below. So let's just say this was our rectangle. If I want to revolve this around the x-axis, it's going to look like a washer like this. So if I want to find just the area so I can find the volume, if I try to find the area of this washer here, the area of a circle is pi r squared. I would find the area of the largest circle and then subtract it with the area of the smaller circle. We're going to use a similar sort of thing when we are finding the volume, which is this equation right here. And this is what we're going to use for our washer method. You have the pi r squared. And I'm kind of looking at this set over here. If I were to factor the pi out, I got r squared minus small r squared. This is the variation that we have for our integral. We have the outside function minus the inside function, and you both square them. So for example, let's just say that we had a linear line and a quadratic, and we're bounded in such a way that we get this shaded region. If I want to revolve this around the x-axis, this is the picture that we would get. So we kind of have a hole in the middle from our gap over here. So here's your summary of the washer method. If we are going to rotate around the horizontal axis, we're going to use this one in terms of x. If we are revolving around a vertical axis, we're going to use this one, which is in terms of y. So here are your steps to finding the volume of a solid using the washer method. First, you want to draw a picture and shade the region that we're going to revolve. Then we want to find r, the distance between the axis of revolution and the outside of the region. Then we want to find the other r, the radius, the smaller radius, and that's the distance between the axis of revolution and the inside of the region. Then you want to find the area of the base of one washer by substituting your expression for r into r into the formula for the area, multiply it by dx, and then integrate it. So let's look at example 2. Find the volume of the solid generated by rotating the region bounded by y equals x equals 0, and y equals x minus 1 squared plus 1. We're rotating about the x-axis. So we already have the picture in the shaded region, so step 2 is find r. And you just need to think about, okay, what is the outside function? And if we are rotating this way, around the x-axis, this one here is going to be our outside function then. And this would be the inside function. That would be the smaller part here of your washer. So this is your r, this is your big R. So the big R is on the outside, and that equation is x minus 1 squared plus 1. We are rotating around 0, so minus 0, which is the x-axis. Little r is going to be x minus the axis we're going to revolve around, which is just 0. So your volume then is, our bounds are from 0 to 1, and remember this is in terms of x. Then according to the formula, we multiply by pi, and it'll be r squared, the big R squared, minus the little r squared dx. We can put this into our graphing calculator to figure out the integral of this, which is going to be 4.817. So in this case, we want to use our washer method because when we revolve around the x-axis, this part over here is the hole. And when we're doing the disk method, there is no hole at all. So for example 3, picture's already given to us. We want to find r, the big R, which is the outside radius, little r is the inside radius. So if I'm revolving around the x-axis, this is going to be on the outside, and then this one's going to be on the inside. So this blue is going to be my big R, which is 2. I'm revolving around the x-axis, so that's minus 0. Then little r, it's that light blue one, x squared minus 2x plus 2, and then I'm revolving around the x-axis, so I subtract 0 from that. We have pi, integral from 0 to 2, looking at our left and right hand bounds. That'll be a big R squared minus little r squared dx. Again, you can put this into your calculator to find the integral, which is 13.404. Example 4 is a little different here because we are going to rotate around the line y equals -1, which is down here. So we are still rotating horizontal axes. So we will make sure everything's in terms of x. I need to find my outer radius and the inner radius. Looks like the outer is going to be this one here because I'm revolving around y equals -1. So that is going to be root x minus, and then the line that we're rotating around is -1. Then the inner radius is 1 over x minus the line we are rotating around, which is -1. We put into our formula here. Our bounds are from 1 to 4, our most left and most right bounds, and then we're going to have r squared, big R squared, minus little r squared dx. You put this in the online calculator or in your graphing calculator. It's going to be 41.817. Here's example 5. In this case, we probably want to make this all in terms of y because we're rotating on a vertical line now. That's our line of rotation. And we're going this way around. So this means that this is your outer radius and the light blue one here is your inner radius. Okay, so that equation is y equals x squared, but we want in terms of y, so we're going to square root both sides. So we have the root of y is x. And then for this one, if I want this in terms of all in terms of y, then I'm going to square both sides to get y squared is equal to x. So the outer radius is the dark blue one. This is going to be root y minus our line of rotation is the y-axis, so that is 0. So x equals 0. Little r is our light blue one, which is y squared. Again, minus 0 because we are rotating around the y-axis. Our bounds, we're looking from the lowest y value to the highest y value. So that's from 0 to 1. Then we have big R squared, in other words just y, minus our little r squared, dy. Put this into the calculator, this will be 0.942. Example 6. We're going to rotate around x equals -2. And that's this line over here. So it's a vertical line. So that means we want to change everything so it's in terms of y. And this is going to rotate around like this. Which means this is your outer radius. This one's your inner radius. Now I'm going to rearrange some things because I have to have everything in terms of y. And square root both sides and get root y is equal to x. That's the only one I really need to change. This is my outer radius, so that's root y minus the line of rotation, which is -2. Then the small r is our green line here, that's the inner radius, which is just 0, because it's x equals 0. That's the line. And then minus our line of rotation. Put into the formula, our bounds are the smallest y value and the largest y value. Big R squared is root y plus 2. Small r is 2. I'm going to square that. And dy. Put this into our online calculator. You should get 92.153. Example 7. Find the volume of the solid generated by rotating the region bounded by y equals 2 root x, y equals 4, x equals 0 around the line, x equals 4. Another vertical line, which means everything should be in terms of y. I'm going to rewrite this. I can divide both sides by 2, so we get y over 2 is equal to root of x, and then square both sides. So then we have y squared over 4 is equal to x. Okay. So our outside function here should be the line, this blue line here, and our inner radius would be this light blue one. You need to be careful with this one. We'll show you why in just a moment, but this is going to be the line we are revolving around minus the most outer line, which is x equals 0. And the reason why we're doing that, we're trying to find the distance between here and here, which is clearly 4. And the other ones, the reason why we did the function minus and the line rotating around is we're trying to find the distance from, let's say, somewhere around here, which is the root of y, to this distance here. So essentially, we could also say that's root y, which is this region here, plus this region here, and we know that's 2. And that's how it worked that way. So for this one, because it's a positive line on the other side of the y-axis, you have to be a bit careful of the order. So same sort of thing, if I want to find the distance between here and here, it's going to be 4 minus the equation of that line, which is y squared over 4. And then now we can put into our volume equation. It's going from 0 to 4. Our smallest y value to the highest y value. Big R squared minus small r squared. dy. This will be about 93.829. Here's the last example. And we are going to revolve around the x-axis and the y-axis, the line y equals 8, and the line x equals 2. So if we're going to revolve around the x-axis, we can use the disk method here, because if I revolve around the x-axis, there are no gaps along the bottom. So that means we're not going to have a hole, so we're using the disk method. So R is the equation, the top minus the bottom. Our bottom is just 0, so what the top is 2x squared. Our formula for using this disk method is pi, our bounds, the most left right to the most right x value, so that's 0 to 2. Then our r squared, so 2x squared all squared dx, which is about 80.425. Now we are going to revolve around the y-axis, and in this case I'm going to use the washer method because there's this big gap here. It's going to create the hole for your washer. We're revolving around like this, which means this line is the outer and this one is the inner. So our big R then is going to be 2 minus 0. Our small r, which is our light blue one, has to be in terms of y, so we have to rewrite this one as the root of y over 2 is equal to x. Okay, so our light blue one is the root of y over 2 minus 0, because we're revolving around the y-axis. And we have vertical lines, so remember to change everything in terms of y. Then our formula is pi. We have to look at the smallest y value to the highest y value. Our smallest y value is 0, our highest is 8. It'll be big R squared minus the small r squared dy, which is about 50.265. Moving on to C, we're going to revolve around y equals 8, which is up here. So we're revolving around this way. Again, we're going to use the washer method because we have this huge gap in here. Our most outer, when we revolve around y equals 8, is 0. And our inner one is going to be 2x squared. Now you want to be careful on how you place the order of this. So for this one, if you want to find the distance between here and here, it's going to be 8 minus our x-axis line, which is 0. And if I want to find little r and find the distances between here, this is going to be 8 minus that function, which is 2x squared. So you're revolving this pi. Your bounds are from 0 to 2, your most left bound and most right bound. Big R squared, which is 8 minus little r, all squared, dx. And this is 187.656. The very last example, we're going to revolve around x equals 2. So we are going to be using the disk method because if we wrap this around, there are no gaps to create the washer. If you're using the disk method, it's going to be the right function minus the left function. Or it could be the right line minus the left line. So our most right is going to be 2. Our most left is this one here. And we are going around a vertical line, so it has to be in terms of y. I'm going to put it into the formula. Our bounds are from 0 to 8. So look for the smallest y value to the highest y value. This is about 16.755.